you have to be little bit theoretical. Initial introduction is little bit theoretical. So you have to bear with that. So almost all algorithms we have studied thus far have been polynomial time algorithms. Many times we mentioned in the class that polynomial time, this term is very important. Polynomial time, polytime, sometimes it is referred as polytime in short, which means O n to the power k. N is the input. Normally the value of k, as I said, 1, 2, 3, up to 4 it is okay. Once it is beyond, I mean going beyond 4 and 5, and then it goes to exponential, which is 2 to the power n, 5 to the power n, such kind, e to the power x format. If it goes, that means it is exponential. So the difference is clear. Once it is exponential means time is more time, and it is polynomial means time is less. In the sense you will be able to see the output very quickly. So when this algorithm design thing was happening, nowadays algorithm design technique, as I said, it has lost its charm. Okay, because of big data technology, people are more concentrating on storage and how to store the data. Earlier people used to develop algorithms, quicker algorithm, people are interested. Now they are not that much, but still it is there. We will see that. But concentration has gone to store more data and how to accommodate the data because of the big data. All these social networks and then e-commerce site, they are generating a lot of data. So people botheration is not how to develop efficient algorithm, rather first let us store the data, then we will think about the efficient algorithm. That's why in DBMS subject also, you will, when you study DBMS, you will find that whole DBMS subjects will be SQL, and the last unit is no SQL. So we don't need any SQL. So first is efficiency, forget, we don't need any SQL. So that means structure query language is not required because data is gone out of hand. We are not able to store, manage the data. Management of the data is important rather than designing an efficient algorithm. But when in the 70s and 60s, this quick, people used to say my algorithm is quick. So quicker term, that means whether your algorithm is quick, unlike Donald J. Knuth, you know, Professor Knuth is a pioneer in algorithm development. He has 5 volumes, I told you, right? Volume 1 to 5, Art of Computer Programming. So he is regarded as one of the best in computer science. So he said that quicker algorithm, quick sort, merge sort, n log n, theta n log n, such kind of discussions has a lot of value. But now in 2006 onwards, things has gone out of hand. People are talking about AI. Today I came to know there is a bot called GB bot or something. AI GB bot has been invented, and that can generate anything. You ask anything, it will tell you the articles, whatever you want, it will be able to do. That means down the line 5 years, you can imagine that even Google will be also obsolete. That AI can generate data, article, whatever you want, they will generate. So it is moving towards artificial intelligence. Okay. So but quicker algorithms earlier means what? Polynomial time is the quick thing. Whether your algorithm is quicker means O n to the power k is the time. But sooner we have seen that time has gone out of hand and it is exponential by nature. So once exponential time comes, that means if you write an algorithm X, which takes a lot of time, has no meaning to us. If it takes 2 days, 3 days, also okay. 3 days, sometimes students will say, my algorithm running in Google Colab for 3 days and I got the output. That is okay. But if somebody said 3 months, so you are not interested in that. So writing algorithm X is not important. Important whether it is quick or not, that too in polynomial time. So once it is going towards exponential means things is not interesting. We are not interested in that. So on this whole exponential drama is there. People say that it is. So that means what? We are moving towards unsolvability. Okay, unsolvability is a very vague term. Unsolvable. Problem is not solvable in polynomial time. That is what people say. So in poly time, it is not solvable. So this is so, but we are ignoring this part. But if you see the scale from 1 to 10, surprisingly, from 1 to 10, 30% problems are decision problem. Remaining all are undecidable problems or unsolvable problem. That means majority of the problems are unsolvable. Nobody is able to deal with it. It's like a cancer. Everywhere cancer is there in all subjects. In physics, you have quantum what is that Bose-Einstein theory on Higgs boson. So people are not able to understand what is there in black hole theory. Physicists, so black hole theory, nobody knows what is going on. So this part of that stuff is that thing whether people don't have any control that much. So remaining 30%, finding GCD, finding these, finding Hamiltonian cycle with a constraint, we are only considering 30%. Remaining 70% is totally out of reach. And surprisingly, maximum 70% problems are there. So what to do with that problem, we will discuss later on. Yes. So majority of the problems are unsolvable in polynomial time, that nobody discuss in the engineering course. Engineering course, you are not focusing into this part, rather you are focusing here. Okay, this is the background. So based on this thing, we have this unsolvable thing, unsolvable, and then unsolvable means it is exponential by nature, which sometimes called non-polynomial, sometimes it is called super polynomial, exponential. Okay, but as you remember that if it is O n to the power k or theta n to the power k and k is up to, let's say, O n cube n to the power 4, it is okay in an industry level, but beyond that it is different. So based on this concept, one question I think can be fixed in Terment. You can just check how much this time complexity varying. Let's say n value you take 100, and then n to the power 100 you are taking, and then exponentially also you are increasing, let's say 2 to the power 100. So how long these things will suddenly, you see this exponential, suddenly one particular point it will grow like this, and it will be much more beyond this n to the power thing. So n will not be able to catch up this exponential graph. Okay, so polynomial, non-polynomial has lot of, heavy difference. You will find sharp difference after some point of time. You will see that once you increase the input size. So this is the background. So there are problems that can be solved, but not in time in polynomial. Now another thing is that if you are not able to solve in polynomial time, then we are not interested in. So for any constant k, generally we think the problem that are solvable in polynomial time algorithm are been tractable problem. So if you are able to solve this 20%, 30% problem, these are called tractable. I am able to solve this problem, so I call it tractable. Sometimes they call it decidable problem. I am able to write some algorithm which will be solving the problem, or easy problem. Okay, easy problem. And the problem that requires super polynomial time as being an intractable problem or undecidable problem, or sometimes it is mentioned in hard problem. So hard problem is actually, it is hard in the sense you are not in polynomial time, it is exponential time, that is called hardness. Okay, so this whole hardness things has lot of, this whole unit is dedicated to these hard problems and all this. Okay, but where is the catch? Catch is that no polynomial, so this is the background. Now suddenly they are making one statement that no polynomial time algorithm has yet been discovered for NP complete problems, nor has anyone able to solve that no polynomial time algorithm can exist for any of them. Meaning is that, another thing is that, so this solvable problem that is 30% wala, these problems are termed as P problem, capital P. P stands for polynomial, and these non-solvable problems refer to NP. NP stands for non-deterministic polynomial. We will come to it. What is the background? Everything I will tell first class. So I have the liberty to tell you everything. So this is NP problem, non-deterministic polynomial. This is polynomial. Okay. So this non-deterministic polynomial thing, actually why it is spelled, earlier you know that Turing was there, Alan Turing. So another interesting thing is that these 70% problems which are unsolvable, we call it NP. Sometimes we call it NP. NP is there, but then hardness comes and it becomes NP complete. We'll come to it, NP complete. Let's assume that we have NP complete set. Nobody is able to peep into here. Nobody is able to solve it in polynomial time. But the beauty is that these problems are many, and people believe that these problems are also connected to each other. That means if you solve one problem, suddenly the chain will be broken. But nobody is able to come this far and able to crack any one of these problems in polynomial time. But they are believing that these problems are connected to each other. I will give you an example. Let's say this problem is clique problem. There is a problem in our syllabus, clique problem, and then clique to vertex cover problem is another problem. What is the significance? You can ask, what is the significance of vertex cover problem? Okay, vertex cover, one simple example I will give you. One example of NP complete problem is vertex cover. Let's say it's a hexagon, and in this hexagon, all this thing complete graph. Okay, so vertex cover problem means you have to find the vertices. First of all, you have to find the vertices which cover all the edges. Edges in one of the side of the edges is covered. That is vertex cover. Okay. So you can find vertex cover. Let's say this is A, B, C, D, E, F. So you can say A, B, C, D, E, F is a vertex cover. Yes, it is covering all the edges, but that is not the catch. Catch is that you have to find the minimum number of vertices. You have to find the minimum number of vertices which cover all the edges. Okay. So which are the vertices will be? How many vertices? If I say A is covering this one, this edge, and this edge. And if I say D is not there. Let's say E is covering this, and then C. A, E, C is there. If I choose these three vertices, all the edges incidents are covered. Yes or no? So this is minimum vertex cover. That means the catch is that you have to find vertex cover and then minimum vertex. So it's a minimization problem. Why this vertex cover problem may be helpful? This when this last time when this attack happened in Uri. So there is a bunkers in this enemy side. So the fighter jet has to go there and they have to bomb those locations which are heavily loaded with resources from the heavily loaded resources, so that the mobilization happens. So obviously the Indian Army or the Indian Air Force will be bombing those bunkers having highly resourceful. So this is one of the application of vertex cover. Okay, they have to choose minimum number of vertices so that bombard happen and all enemy front got destroyed, so that everything got destroyed. Okay, so this is the vertex cover. So vertex cover problem is another hard problem. Okay, it is obviously NP problem, those things are there, but nobody is able to solve this problem in polynomial time. Okay, so this is the background. Now another interesting catch is that P problem you understood, the easy problem. NP problem is somewhat hard problem, but nobody also know whether P equal to NP or not. That means whether P set is, first of all I have to tell you what is P. P problem is the easy problem, and NP problem is that you cannot get the solution in polynomial. Achha, what to do with the NP problem? If I am not getting the solution in NP problem, what I have to do? What people say that, okay, if I am not getting solution, I will verify. Just verify. Meaning is that here let's say it is vertex cover with 6 vertices. If I give you the edge, vertex A, vertex E and vertex C, and if I ask you to just verify whether they are connected and whether these things are happening, you can quickly go and check the connections only. Not the solution, but some part of the thing. So that is called verification. So one thing is the solution, another one is the verification. Solution is a big thing. If I ask you to find solution of vertex cover, this becomes a big thing, big task. But if I ask just verify, that becomes a small task. Okay, so this small task can be done in O(n to the power k) most of the case. So if it is a small task and if it is verifiable, then I will call it a NP problem. Okay, let's say solution is not possible, but whether you are able to verify it in polynomial time or not, that is possible, then it is called a NP problem. Okay, so this and P problem, full solutions are available for P problem, whole solutions are available in polynomial time. But in case of NP problem, only the verification algorithms are available. So you have to understand this verification. These are there in the slides. We'll come to it. So this is the background of NP. Now NP you understood, P you understood. Then another set comes which is called NP complete. Just now I said this NP complete set is also there. That means the combination of all NP complete problem they have put together in a set and they call it NP complete problem. That means in NP complete problem, if you crack one problem in polynomial time, that means if you are getting solution, you will get all other solutions also. Okay, so this is there, and then finally as a NP complete also consider NP hard and all. When we will come to the basic definition, we will see that. Now the NP complete problems are particularly tantalizing because they seems on a surface to be similar from that we know solve in polynomial time. Now you see there are some problems which are called sound similar problems. Okay, sound. One thing you understood that NP complete and NP hard. These things are not solvable in polynomial time. Okay, not solvable in poly time. There's an exponential results you will get. Only P problem that we are seeing in the engineering course, which like finding GCD and all other things, it's quick results and it is O(n to the power k). It is happening, but this whole bunch is not happening in O(n to the power k). Rather, it is happening in exponential nature. Okay, this is the group. Now you see sound similar problem. That means sometimes you will come across some problem which will sound similar, but they are way different when you are going to solve it. Example, finding shortest path. Okay, let's say I'm giving you a graph and then I'm asking you to find shortest path of this from A, B, C, D, and then I'm putting some weight. You will be able to find the shortest path. Okay, but when I call longest path, things become so shortest path. Writing an algorithm for shortest path could happen in O(n to the power k), but when I find longest path, this may not happen. So shortest path, longest path, both sound similar. But one problem is solvable, another one is way hard, heavy hard. It's not possible. So sound similar problem. Okay. So and then you have Euler-Tour and Hamiltonian cycle. See, Euler-Tour also graph traversal related algorithm. Hamiltonian cycle also graph traversal related algorithm. Both are similar type of algorithm. Once graph. Okay. Now sometimes the Euler graph also there. Euler. No problem. Okay. So Hamiltonian cycle and Euler-Tour, these things are there. So if you see, this is the Euler-Tour. So Euler-Tour basically slight difference in the definition. You see here I am starting. I am asking you to visit all the vertices, all the edges I am asking you to visit in case of Euler-Tour, which is an easy task. Why? Because you are visiting first this, then you are coming this, and then coming here, then coming here, and then going back again here and again visiting. So going back is allowed in Euler-Tour. Okay, going back. Any number of times. This will be used later on when we will discuss about approximation algorithm. Euler-Tour will come again. So this is Euler-Tour. This is just a simple tour you are doing. So this is one edge 1 has been visited, 2 has been visited, 6, and then again 6 you are visiting. So again is allowed here. Euler-Tour is an easy thing. Possibility is that you will find O into the power k polynomial. Solution you will directly able to write. That means you will able to write an algorithm which will be solve this problem. But if I just slightly change the definition of this touring thing, saying that it will start from a vertex and it will visit all the vertices exactly once, if I just put a simple constraint, exactly once, then it becomes a Hamiltonian cycle, or in short it calls Ham cycle. Ham cycle, if you start it from here, this, like that you are visiting. No vertices you are visiting twice, and then finally you are coming to the source vertex. So slightly change exactly once. Whereas in case of Euler-Tour, it is not exactly one, any number of times you want. So this problem is Euler-Tour, which is a P problem. This problem, which is Hamiltonian cycle, it is a NP complete problem. That means it's hard as well as NP. You will come to the definition of NP complete, official definition. This is you remember, this is a hard problem. Okay, Hamiltonian cycle. Some of you are presenting also Hamiltonian cycle in. So this is there. So sound similar, but way different. Okay, sound similar, way different. Euler-Tour and Hamiltonian cycle, slight change in the definition, things got very difficult. So Euler-Tour can be done in OE time. Hamiltonian cycle, I think they didn't have given. It is much more time it takes, exponential time only. Then there is another concept which is called 2 CNF satisfiability, 3 CNF satisfiability. Now satisfiability has got heavy, I mean this terminology we will be using, because every time you have a graph, we cannot do anything with the graph. It has to convert it to circuit. Graph will be converted to circuit. Then you have to check whether circuit is working or not. That means for a specific input, because you will be having a graph, it will be directly covered. So this is a graph. Can I not convert this graph into a circuit? I can do. Just that these will be gates and all, and then connections can be checked. So when I say graph to circuit, and then I say 2 CNF satisfiability and 3 CNF satisfiability. 2 CNF satisfiability is a P problem. Meaning is that when you have these clauses, so this is called conjunctive normal form. When you have these clauses, you have only two literals here. Okay, two literals. Just that if you increase the literals here with another one, if you make it 3, this problem becomes unsolvable in polynomial time. So 2 CNF, just if you increase 3, it becomes out of hand. You are not able to solve it. Okay, so 2 CNF satisfiability and 3 CNF satisfiability. In short, it is called 2 SAT, and in short, it is called 3 SAT. Satisfiability problem. Okay, so these things will come. So NP complete problem we have discussed. NP complete, NPC. So what is NPC? That first of all, it is not, you are not able to solve it. So it is a problem for which correctness of each solution can be verified quickly. So here this verification term comes. Sometimes what happens, we use this verification term as certificate. Okay, this is nothing but a verification, means it's a certificate. Certificate means, let's say for some particular input x1 equal to 0, x2 equal to 1 and x3 equal to 0. This is a certificate for a particular graph. For this input, a graph becomes Boolean 1, output is 1. So this will become a certificate. So it is a problem which correctness verified quickly, polynomial time. Quickly means polynomial. Quickly is a term which is used correspond to O n to the power k. And a brute force algorithm can be found solution trying all possible. So when it goes to brute force, it is not NP. Okay, it is not P. It is a NP problem when it goes to brute force. Okay, the problem can be used simulate every other problem for which it can verify quickly that a solution is correct. In this sense, NP complete problems are the hardest of the problems of which solution can be verified quickly. So one thing you remember when I say NP complete or NP, always remember in mind that this is verification. Verification in polytime is possible. Verification in polytime is, that means only verification is allowed. Okay, when I say capital P, it is a polynomial, solution is possible in polynomial. Example of NP complete, just now I gave many other examples are there. Okay, so this is there. Will come NPC by definition, it has to also, so hard problem you understood, we will come to it slowly.
So NP hard is possible to verify?
NP hard is possible to verify.
Similar to NP.
NP complete is, I will come first, it is P set, okay, which is the most smallest set, which consider all the easy problem. That means solution polynomial time is possible O n to the power k. Okay, solution itself is possible, like finding GCD of two numbers. And then NP, which is verification in polytime, is possible. Verification in polytime, that means verification in O n to the power k. When I say NP hard, things become little bit tougher. That means we have NP plus hard, both definition has to be satisfied. I will tell you what is hard definition, mathematical definition of hard. NPC is reduction will come here. So basically just I am trying to tell you first the set, try to let us have an outlook of the whole problem set. P, the easiest one, solution is possible in polynomial. NP, solution is not possible, verification is possible. NP hard little bit more constant than NP, where this hardness definition has also to be satisfied. That means it has to be said NP and it has to be NP hard both. If these both conditions satisfied, then problem will be NP complete. Okay, so then reduction in everything will come. I will tell you the definition. These are all set things. So, and also don't not try to visualize this whole thing in terms of set. Why I am saying you should not visualize. Another thing is that if you have a problem in P, whether verification in polynomial is also possible for P? Yes, verification is the easiest thing. So if I say, so P is easy problem, but then NP set is another set, big set. Okay, NP is the set, and then hard is also there somehow. What I am trying to say, don't try to visualize this in terms of set. These are not set. Okay, so you cannot say that P is here, NP is a bigger set, so P is a smaller set. It should be. This is the problem. Nobody knows whether P should be inside or P should be not equal to NP. Nobody is able to prove that P is also not equal to, nothing has been proved here. So these are all things which is yet to be done. Okay, so this is the thing. So you can see that here they have given, few scientists believe that P is equal to NP, some scientists believe that P is not equal to NP. Total confusion is there. Okay, so you can, if let's say somebody prove that P is equal to NP, then everything will collapse. Whole computer science 90% will collapse the day you prove that P is equal to NP. So this P is equal to NP means everything will change, but nobody has able to done that. So 𝐂𝐨 Mathematical Institute is offering 1 million reward for this proof. If you can prove, take one problem, let's say Hamiltonian cycle problem, TSP, different strategy by which we cannot do the full solution, but we will keep the patient alive if it is a cancer. Okay, so this is there. So you see, these are the problems which are NP complete, and as I said, as I told you that these problems are related to each other. You see here, this is satisfied. Actually, the main things problem happened. Why? You know Alan Turing. All of you know Alan Turing, who is considered the father of computer science. He has developed Turing machine. Turing machine, all of you know. What is the Turing machine? All of you know. Turing machine is the machine, primitive machines, which if you can solve any problem mathematically, let's say you have given a proof, correctness, everything is there. Turing machine should be officially able to solve that problem. Turing machine is a small machine. I think I have this Turing. I will show you. This is a small machine which parts the strings one by one. Some strings you will get, it will parse and give it yes. Answer is the string has been. Some string won't be passed. Okay. So Turing machine is that means A plus B, small program you can do. Then the language that I have given, A to the power n, B to the power n. One day I was talking about it. Actually, in World War II, he died. So there is a movie called Imitation Game. You all should imitation game on movies there. You see that movie, you'll understand. World War II, he has been given to crack the cipher text, plain text and cryptography. So he developed one machine called Enigma machine and he solved it. And he said that I will be able to crack this P equal to NP. But in between he died. Afterwards, nobody is able to do. He because of his death, everything, the chaos happened. Okay, so these are the problem, Boolean satisfiability problem, which in short called SAT. SAT problem is NP complete, knapsack problem, Hamiltonian path problem, subgraph, subset sum, clique problem. These are all NP complete problems. Okay, these problems nobody is able to solve in polynomial time. So this is the thing. So you can see that, as I said, there are another interesting property of NP complete. So NP complete, for the time being, you just imagine that NP complete problems are those which will be NP as well as NP hard. Okay, and for the hardness, you imagine that this is much more tougher than NP. Okay, more stricter problem. The definition. So for this understanding NP and NP hard, you have to understand reduction, which next class I will be starting, not today. Reduction algorithm. That means reduction in polynomial time is possible now. Let's say I have given you a problem pi 1, which I am asking whether it is in NP complete or not. And how to do that? You have to take another problem pi 2, which you already know in NP. You have to reduce this problem in polynomial time. If you can reduce, that means let's say one program is there with you, which solution is available. I have given to crack another problem where you are using this program, the given program, and that to happen in polynomial. Once again, pi 1, which is in set NP, this pi 1 should be polynomial reducible to pi 2. If this is the case, then I will call pi 2 as NP hard. This is the official definition. That means you take one problem which solution is already known in polynomial time and the reduction also in polynomial time, then you can say something about NP pi 2 as NP hard. Okay, but don't conclude anything about that pi 1 is equal to pi 2, pi 2 is equal to equally hard. Don't, nothing. Just you can say pi 2 is NP hard. Okay, pi 2 is NP hard. Pi 2 is NP hard is much more stricter. So if you look at it, NP complete said here, hard problems, I don't know where it is. Hard problems set wise, actually we should not visualize. Hard problems may be outside of this, not a set team. But for the easiness, we used to visualize these problems like this. But always remember, P is easy, NP is little bit tough, NP hard is much more tougher. NP plus NP hard combinedly gives us a set of problems which is called NP complete problem. Now the beauty is that this is the NP complete whole problem set. Some problems that they have given, many more other problems are also there. So they have started with the Boolean circuit SAT. Circuit SAT is the satisfiability problem, which we'll discuss. Circuit SAT to SAT, they have reduced. SAT to 3 SAT is possible. These reductions are possible. Reductions are going on. So they are somehow, these problems are somehow related to each other. But related to each other, this has been proved. So this set, they have named it NP complete set. This is the properties. But nobody is able to take one problem out of it and can reduce it to P. That is not happening. Neither it is happening that people are not able to say whether P not equal to NP, nor they are able to say P equal to NP. So everywhere confusion remains. Okay. So that's why these things happen. So this is the background of NP complete set. What we will do to deal with these problems? As I said, first thing is that we can approximate it. Approximate in which time? Yes. Approximate in polynomial time. Okay. Approximate in polynomial. That means let's say some algorithm is given 5 to the power n time complexity. Problem X. If you are having solution for problem X, it is giving 5 to the power n. Just imaginary purpose we are saying. You will be approximating and you will be making it something like this, like say 5 to the power n, like something 2 to the power n, no, like it will be near to 5 to the power n. Okay, near to 5 to, that will be called approximation. That has to happen in polynomial time. Once you prescribe an approximation algorithm, that has to happen in polynomial time. This is the first approach. This is there in our syllabus. Second approach is randomization. Randomness to get faster average running time. Nothing is happening. No solution is happening. Quicksort is solution is possible. Randomly we will do something. We will try to reduce the time, but we won't get actual solution. Something better improvement. Randomness. Second thing is the restriction. Then parameterization. Many people works in parameterization. They do some fast algorithm. If the certain parameter of the input are fixed, So parameterization may be, this prime numbers. What do you think? Prime numbers are NP or NP complete? Is it a hard problem or it's a solvable problems? That means given the prime number of biggest length, if I ask you to crack it, write an algorithm, whether you will be able to write prime numbers, you will write. But the student used to write program, find the number, prime number, right? 7, 29. But given the number of length of the number is huge, you won't be able to write an algorithm in polynomial time. So as I said in the first class, Mahindra Agarwal from IIT Kanpur, they have proposed one paper called primes are in P. What they did, they put some constraint here in the prime numbers. Constraint is there and they solved it in and some logarithmic format they have bring down. So they are telling this is somewhat P. Hamiltonian cycle is also there. So this is a cycle starting exactly 1 every time you are visiting all the vertices, exactly 1. What they put here, they said, okay, because Hamiltonian cycle is unsolvable in polynomial time, I will put triangle inequality in it. Triangle inequality. That means 2 edges are greater than 1 edge. This triangle, every triangle that is forms, if you put A plus B and this is C, so A plus B always will be greater than C. This concept, if you put here, this restriction, then you will be able to, you will be able to solve it in polynomial time. This is called Hamiltonian cycle, traveling salespersons, okay? So these are there. Heuristic methods are available. Heuristic method, one of the method we have start A star algorithm. A star algorithm actually it is, they have, so A star algorithm actually heuristic. Because every time you remember here to here going, every time I am putting some heuristic here. Somehow I am trying to solve this problem with my own intuition and other methods. That expert will provide the heuristic values for each node so that one person can start from here and he can reach the destination. Trying to solve this problem in some consolation prize. Okay. So this is there.